Hi, I'm Josh from Grey Matter Robotics. This year's FTC competition involves a lot of mathematical modelling, and we found that with the help of some simple mechanics that we're able to complete some of the tasks more efficiently and know what we're up against and how better to design our robot. One of the obstacles that you might have noticed in this year's competition is a large ramp with an 18-degree gradient. Now, with this, we worried that our robot would not be able to move the bowling ball up to the top of the ramp, and we thought this was quite an important part of the competition and an area that we wanted to try and score as many points in as we could. And so, to work out if our robot was going to be capable of doing so, we modelled it using some simple mechanics we learnt in a maths class. Firstly, we need to convert some of the units into the SI units that we'd use to get an appropriate answer. And so we have to take the bowling ball's mass, which is 6 pounds, and convert that into kilograms. Now there are 2.2 pounds in a kilogram, so the bowling ball has a mass of approximately 2.7 kilograms. Next we need to draw a diagram to show what the model is going to consist of. Here we have the ramp shown here with an angle here of 18 degrees. This is known as theta here. We're going to use the formula mg times cos theta times cos 90 minus theta is equal to the mass times the acceleration. Now, the mass here is the mass of the bowling ball, which is 2.7 kilograms. The g is gravity, or acceleration due to gravity, which is 9.81 meters per second squared. The cos 90 minus theta gives you the fraction of the acceleration due to gravity, which is going to be exerted on the bowling ball, as if it was falling straight down it would accelerate at a rate of 9.81 meters per second. However, it's rolling along a slope. We're going to ignore friction in this, as a ball rolling along a smooth surface isn't going to exert much friction, but you might want to add another 5 or so % onto your answer to ensure that there would be enough force to overcome the force of friction. Now, the formula here is actually quite a simple one to use. We simply take the mass of the bowling ball, which is 2.7 kilograms, we times that by 9.81, and then by cos 90 minus theta, as theta is equal to 18. Now, if we put this into a calculator, we work out the answer to be 8.2 newtons. Now, newtons is the SI unit of force, and is the same as a kilogram meter per second squared. It's a compound of acceleration and mass, which is obvious from the units we'd used beforehand. Now, this is the amount of force, 8.2 newtons, that a robot would have to exert to stay in equilibrium with the bowling ball. So that's the force that the bowling ball is exerting down the ramp. If a robot was to meet that force, it would not accelerate. Now, as the robot will start off stationary, it won't actually move at all if it exerts 8.2 newtons. To push the bowling ball up the ramp, you need to be exerting a force greater than 8.2 newtons. Now, if we take into account friction and the loss of grip on the ramp, as it's a fairly smooth surface as aforementioned, the robot would have to be probably exerting somewhere around 10 newtons of force in order to comfortably be able to overcome gravity and push the bowling ball up. Another problem with mathematical modelling, or a problem with mathematical modelling, is that sometimes the model can't take into account all of the circumstances, and we found that very easily our robot is able to meet this threshold of around about 10 newtons of force. However, there is a lip at the bottom of the ramp where the ramp doesn't quite touch the ground, and we found that this was the largest area of issue for our robot, and that although when we're on the ramp, the robot is perfectly capable of moving the ball up, getting onto the ramp was our largest challenge. There are many areas in robotics and other types of engineering where mechanics is an obvious and useful tool to help you model some of the problems. This is one of those areas, but there are many others even in this year's competition. I hope this has helped you, and good luck in the rest of the competition from Grey Matter Robotics. Bye.